Hello everyone and welcome to Texas Tech University's Project Lab 1 tutorial videos. I am one of the tutors for this course. My name is Daniel, and in this video I'm going to be showing you how to use the 7-segment display on the BASYS2 board using the multiplexing method. Alright, and to get started we're going to go to Google. And we're going to search BASYS2 7-segment multiplexing. And this will bring you to a few links. First I wanted to just show you stackoverflow.com. Just wanted to mention that they are a great resource for example code and tutorials on how to create modules and do a bunch of different stuff on the BASYS2 board. But the one we're going to be looking at today is from simplefpga.blogspot.com, and it says learn Verilog by examples 7-segment LED multiplexing circuit. So this website does a great job on explaining how the multiplexing works on the BASYS2 board. It talks about the way to multiplexing using an 18-bit counter, and talks about the anode, cathodes, everything that is used with multiplexing and the 7-segment display. So finding example code online is a good way to learn how to create modules and learn how to write Verilog code. But it is important that you actually understand how everything in this code works. If you end up just copying it and you don't know how something works, then you end up not learning how to code and you end up just copying code. So in this video we are going to go through this web page, what everything means, go through this code line by line, and then set it up on our BASYS board and program it using UCF. Alright, so to start we want to look at the BASYS2 board. We'll see that there is 4 digits on the 7-segment display here. And then looking back at the setup, we can see that each digit on the 7-segment display has 8 cathodes. It's a 7-segment plus the decimal point, so that makes 8 cathodes and 1 anode. So without multiplexing, we would have had 8 connections for each one of these digits, which would have ended up having 32 connections and just a lot of in and out inputs, outputs that are unnecessary. So the technique they use here is multiplexing, where you turn on one light at a time, one digit at a time, and you just scroll through it fast enough to make your eyes think that all 4 are being lit up at the same time. And that is done using the counters down below. But first I want to mention that the BASYS2 board, as mentioned here, it is an active low system for the 7-segment display, in which that you need a 0 to turn that segment on. So if we look at the BASYS2 data sheet, so I came to Digital website, hit data sheet for the BASYS2 board, and if we scroll down to the 7-segment part, there we go, we see that this configuration is the common anode setup, and it has a standard 7-segment configuration, in which has this segment is A, this segment is B, C, D, E, F, and G, and then a decimal point. But with that in mind, you can go back to this and see that in this image, in this figure here, it's showing you what is required to light up this 3 on this 0-digit position. So in order for this digit to be turned on, the 0 needs to be there, so that this digit only is turned on, so the rest of these are 1s and they're off. And to create this number 3, we need to turn all of them on except for, let's see, A, B, C, D, E, and F. E and F would be off, and decimal point would be off. So looking at the inputs of the cathodes here, we see that E and F are off and decimal point are off. So that explains this figure, and that's pretty much what we're going to be doing on the BASYS board. Just creating all these data for the inputs and outputs through lookup tables, and I'll cover more of that once we get into the code part. First, we just wanted to talk about the clock on the on the BASYS board, and how we're going to use an 18-bit counter to toggle through each digit here. So if you see here, it says that the refresh rate to create the desired effect of making it look like all four digits are lit up at the same time, we want at least a 100 Hertz refresh rate. So doing a little bit of math, we know we have a 50 megahertz clock on the BASYS2 board. We divide it by 16 bits, so 2 to the 16th, and it comes out to about 800 Hertz. So 800 is close enough to our 1000 goal here. So we will use 16 bits, and we will add 2 bits to toggle through the 4 different digit positions. So what that means, let me open up a calculator real quick. Set it to binary. Here I went to view programmer. So now we have our calculator in binary. So we have a 16-bit counter, so let's fill up our 16-bit. So this fills up and it gets full to 16 bits. So what this means is, for this amount of time while this counter fills up, these 2 additional bits that we added, the 17th and 18th bit, are telling us which digit we are on. So the first time it fills up, the counter fills up, we are at position 0. These 2 are 0, 0. And then we add some time, so let's add another 61, so another 16-bit counter fills up, and we add that. And we see that it moves us to position 0, 1. So that would move us from digit 0 to digit 1. And then we add again another 16 bits. So the counter fills up again, and that switches us to position 2. So now we're at position 1, 0, position 2. And that moves us to digit 2. And again, you would add another 16 bits, and moves us to position 3. And if you continue adding, you'll see that it just cycles back through to position 0. So now it's 0, 0. We only have 18 bits in our counter, so this 19-bit doesn't matter. It's back to 0, 0, and if you keep adding, it will cycle through position 1, 2, 3, 0, 1, 2, and 3 sequentially. So it'll move 0, 1, 2, 3, and 0, 1, 2, 3 as many times as you add the 16-bit counter. So that creates a little bit of a delay between each one as it switches, but it also switches fast enough to create the simultaneous effect. Alright, so that explains the 18 bits and the 800 Hertz. So now we can move on to the code here. So to do that, I'm going to open up the Verilog ISE Webpack. I'm going to open up the 32-bit navigator so I can write some code. I'm going to go to File, close that out, File, New Project. I'm going to call this tutorial underscore 7seg, and we want it to be an HDL type. Hit next. Look at the project settings. If you are using your own computer and you have done a Verilog project on your BASYS2 board, then these should all be the same. If you're using one of the lab computers, then you want to make sure you set all of these settings for the specific BASYS2 board and FPGA chip we are using. So hit next and finish, and it'll create this empty project that we can start writing some code to make our 7-segment display work. So what we want to do is come here to the hierarchy and right click inside anywhere in here where it says empty view. So right click, hit new source. We're going to write a Verilog module. We're going to call it tutorial. I know I misspelled the last tutorial. This is tutorial 7seg2. And next, here it wants you to identify your inputs and outputs. For now, we're going to hit next and finish. And it'll create this empty module for you. It creates the regular, the standard header for you. You can fill this out if you want to. Don't change the time scale. And then we want to go back to simplefpga.blogspot.com. And we want to copy everything from line 2 down to line 80. So it's important that you don't copy line 1. You don't want to copy the title. We have our own title. So we will replace everything below the title. Control V. And then you want to make sure that it copied correctly. So you want to make sure that there's no that you only have one end module here, and that it shows it blue like this. And then you can scroll up, and then you want to check that you only have one open parentheses and one closed parentheses that goes with it, and followed by a semicolon. And now we can start looking through this code and make sure that we know how everything works and modifying it to do what we need it to do. Alright, so starting with the inputs, we see there's a clock input and a reset input. This clock input, we will assign it to the 50 megahertz oscillator that is on the BASYS2 board. So that way it acts as the clock that runs this module. And if we look down here, you see that we'll get to this block, but this is using the clock to increment a counter. So this reset is again an input. Since it's not assigned specific size, it is default to 1 bit, so both clock and reset are 1 bit. And reset, as you see down here, will be used to clear the counter if pressed. Alright, so inputs. Now we have this IN0, IN1, IN2, IN3. It says a comment here that these inputs are for each display. So to figure out exactly what they are, we're going to scroll down a little bit, and we'd see that IN0 goes into SSEG here, IN1 goes into SSEG here, 2 here, and 3 here. Alright, so they all go to the same variable called SSEG, but if you look at this AN temp, AN would be referring to the anodes of the digits, and we know that 0 turns the digit on, so we're seeing that this input 0 goes to digit 0, input 1 is the 7-segment pattern that goes to digit 1, and so forth, so on, 2 and 3. Alright, so now we see that N0, N1, N2 is a pattern that goes into the 7-segment of that digit. So if we keep scrolling down a little bit, we see that these become into SSEG, and there's a case statement here that uses SSEG as the argument. And if we look at this right here, we can see that SSEG can be a digit that ranges from 0 to 9. So SSEG can be anything from 0 to 9. However, as the code sits right now, IN0, IN1, IN2, and IN3 are by default 1 bit. So therefore, when IN1, IN2, IN3 go into 7seg there, SSEG here will only be able to use these two positions because the digit can either be only a 0 or a 1. So therefore we can only display a 0 or a 1. So to make sure we can access these remaining options to display everything from a 2 to a 9, we want to make sure that these inputs can hold a value up to 0 through 9. So 10 different values we need. So in order to hold 10 different values, we can assign this to be an array that has position 3 to position 0. So, square bracket. So therefore, giving it 4 positions, 1 would be position 0, 1 would be position 1, 1 position 2, and 1 position 3. And now we can say that each one of these inputs are 4 bits long. Alright, so that solves this issue where we can now display every digit from 0 to 9 instead of just being able to display the first 2. But if we go back and look at our BASYS board, we know we want 4 inputs, and each input has 4 bits in it. So therefore we need 16 total bits that we can change. However, due to the components on the BASYS board, we only have 8 plus 4, 12 inputs that we can change here. We can use the PMOD ports, VGA port, and PSC ports, but that requires a little bit more components, and just for simplicity, we're going to remove some of the inputs so that we can all we have to use is these slide switches here. Alright, so to do that, instead of having 4 inputs of 4 bits each, we are going to delete 2 of the inputs, and now we only have 2 inputs of 4 bits each, totaling of 8, and we can easily use the 8 slide switches that are on the BASYS2 board. Alright, so we deleted IN2 and IN3. Since we deleted inputs, we're going to have to look through the code, so Control F to find this, to open up this finder here, and you can search for IN2, hit enter, and it'll show you everywhere IN2 is used. So click on IN2 here, delete it, replace it with a 0, so that way we can just display a 0 on digit 2 here, and hit next to see if IN2 is used anywhere else. It is not, so now we can search for IN3, hit enter. It shows you where it is used in the code. Again, delete it because we deleted this input and replace it with a 0, and hit next to see if it's used anywhere else. It is not, so we're done with this finder. Alright, so now we are done looking at all the inputs. We know what all the inputs are and what they do, and now we can look at these outputs. This one's pretty trivial. They're called A, B, C, D, E, F, G, and D, P. And the comment tells you that these are the outputs for each individual 7 segment on the 7 segment display. And this one's also pretty trivial. You can see that these are 4 positions for each one of the anodes that corresponds to the digit. So those outputs are these inputs here. So an output from the module goes to the input of the actual 7 segment display itself. Alright, so if we keep scrolling down, the first thing we see is this local parameter. Local parameter is a way to create a variable here we're creating this variable called n, and it holds the value of 18. 18, if you remember, is the number of bits we're going to be using on our counter to create the approximately 1000 hertz multiplex that we are trying to create. So to do that, we do n minus 1 to give us 17, and then the lowest position is 0. So again, we have to count the 0, so therefore total is 18 positions on this array called count. And this will be the counter that will be incrementing the 16 bits, and we'll be evaluating the top 2 bits to move from one digit to another digit to another. Okay, so here, this block right here, it says always at pause edge or pause edge or reset. Always at says that always at when this argument is true, so whenever a positive edge of the clock or a positive edge of the reset is identified, we begin and end this block right here. So this block, all it's doing is incrementing the counter every time the clock ticks. So every time we notice a clock rise, we will increment the counter unless reset is pressed, and then therefore we will reset the counter. So that explains this small block. We can move on down to these 2 registers. This 2 registers, it tells you that it's used to hold some data. In Verilog, you cannot manipulate an output as you would in like this case. In this case, so say we wanted to manipulate the anodes here. So if we're looking at this code, it says always at star. Star says anytime anything happens, so always at anytime anything happens, anytime anything changes, we will begin this block right here. And it is a case statement. It says case count. So this is the argument which says just look at position 1 and position 2 of the counter, which is n minus 1, which is position 17, and position 16. Again, we know that the count goes from 17 down to 0. So we're looking at position 17 and we're looking at position 16. And just as I showed you in the calculator earlier, if they are 0, 0, we're at position 0. And position 0, and we're entering the data coming in from the input. If the counter goes up to 0, 1, we're at position 0, 1 on the digit, and we're entering the pattern coming in from input 1. Here we see that if those 2 bits are in position 2, we're in digit 2, and I hard coded it. We removed the input 2 and we hard coded it to be a 0. Again, same thing here, position 3, and we hard coded it to be 0. So that finishes this entire block. That explains this block of always at star that goes up to here. So just to summarize, this entire block happens anytime anything changes, and it evaluates the top 2 most significant bits of the counter to toggle through the 4 different digits on the BASYS2 board on the 7-segment display. So it encase, and then we assign the variable we created, the temporary variable we created, we assign it to its appropriate output. Again, you can't manipulate outputs directly. If you replace all the AN temps with AN, Verilog gave you all sorts of errors and then won't let you do that. So to get around that, we create registers, and then we assign the register to its appropriate output. Alright, so another temporary register called SSEG temp. Here again, always at star, so anytime anything changes, we will begin and end this case, which says update the 7 segment based on the digit that is in 7 segment, put the appropriate pattern. And immediately following this always at block, you will see this is IN statement that will assign the bit pattern that we want to the appropriate segments that they need to go. Alright, and the last thing you see here is that the decimal point is always turned off. So if you wanted to turn it on, you would just change this to a 0, this 1 right here, to a 0, and it would turn it on, but here we don't need it, so it's turned off. If you wanted to change it based on the pattern that you wanted, here you could just add an 8th bit and do that, and then you would just concatenate the decimal point in here also. Alright, so that pretty much explains the entire module here. The next thing to do, we have adjusted the inputs to use our BASYS board. We have evaluated all the outputs and made sure we understand how everything in the code works. So the next thing we can do is hit save to get rid of the asterisks and synthesize our module. Synthesizing will check for syntax errors and we'll let you know if the module is good to move on to implementation. Here we see that there's a few warnings, but since there's no errors, we can continue to implementation. To do an implementation is where we route all of our inputs and outputs to their location, their appropriate location on the BASYS board. So we would assign the clock to the clock, reset to a button, these to switches, and these to the cathodes, and these to the anode. So to do that, we are going to right click right here, add a new source. This time we're going to do an implementation constraint file. I'm going to call it tutorial underscore SSEG2 underscore UCF. This is a typical naming convention. You name it the same name as your module and then underscore UCF, so that way you know that that's the UCF that goes with that module. Hit next, hit finish, and it should see it connected the UCF to that module, and it opened up this blank UCF file. So to create a UCF, I usually just go to Google and Google BASYS2 master UCF. Click on this link. It brings you to the master UCF for the BASYS2 board. So you can highlight and copy all of this, Control C. Paste it in your blank UCF here, Control V. And now you'll see that most of it is commented out. You want to comment everything out, so anything that is not commented, hit Alt C and it'll comment that. So highlight it, hit Alt C, and it'll comment that. So this shows you every single component that is on the BASYS board. So these are the PMOD ports. It gives you the signal name, and it gives you a little bit more information than you know what to do with right now, but this is still a great place to start for your UCFs because it shows you the location of everything on the board. Alright, so buttons, we are not using any button except for reset, so I will comment these out, Alt C. And in the UCF, we are just routing every input and every output. So let me go comment everything out first, and then we can go through our inputs and outputs and route them to where they need to go. And again, I'm just highlighting, hitting Alt C, and it'll comment that for you. Alright, a few more. go. 7 segs. And clocks up the top. So, oh, alright. Anyway, so now we have our template now, and we can uncomment everything we need. So starting with the first inputs, we need a clock and a reset. So first we will go to this M clock here. We will uncomment this line. Ours is called clock, not M clock. SCLOCK, all lowercase. Location is B8, and the signal name is master clock. Alright, so that's clock. For reset, we're going to use a button. So if you scroll down, we can see, so they usually have, so these are LEDs, these are switches, buttons. Here we go. So these are the buttons. We can remove the comment and replace this with our variable, which is called reset. And now reset is assigned to this location A7. And if we want to see where that is on the board, we just look at our picture, and we see that we assigned it to location A7, which is this button right here. Alright, so that finishes clock and reset. Now we can assign our inputs IN0 and IN1. For those, we said we wanted to use switches, so we'll come here to this switches, highlight it all, Alt-C, actually uncomment is Alt-Shift-C. There you go. Alright, so we uncommented all out, but our switches are called IN0, our inputs are called IN0 and IN1. So here, we're going to start with IN1, position 3, because it only has 4 positions. So we will give each position its own location. So position 2, position 1, and position 0. Same thing with input 0. You will give it each position its own location. So there we go. Input 1 are these 4 switches, and input 2 are these 4 switches. And again, if you wanted to look to see where those switches are on the BASYS board, you would just look at either this location, it says B4, K3, L3, P11, and see that this is K3, L3, P11. So these are the 4 switches that would be going with input 0 here. Or you can just look here where it says SWs. That's the signal name. That is the label that is right next to it. Alright, so we have all of our inputs. Let's go back to our module. So we have designated locations for all of our inputs. Now we move on to our outputs. So these have to go to the 7 segments, right? So let's go back to our master UCF. We can scroll down, scroll up. There they are. It says connected to the 7 segment display. Here it says seg 0 through 7, and we can see that it says cathode A, cathode B, cathode C, cathode D, all the way to decimal point. So these are the ones we need for our cathodes, so we can highlight all these. That one, Alt-Shift-C, uncomment them, and now we put them their appropriate name. So this one is lowercase a, this one is lowercase b, and C, D, E, F, G, and DP. So that finishes those outputs. Now we have to assign the outputs for the anodes. And AN has, again, 4 positions. So if we go here, we can see that these are the anodes. Go ahead and uncomment those, Alt-Shift-C. And they are already labeled what they're supposed to be. AN position 3, AN position 2, AN position 1, and AN position 0. So those are done. And we go back to our module. We see that now we have routed all of our inputs and all of our outputs. Our UCF is finished. We can go ahead and save this. This is already saved, so the next step is to implement design. So double click on make sure this is highlighted and double click on implement design. It'll run that. It should give you a green check mark.